Hello everyone, and thank you very much for watching this very short presentation on how not to use total focusing method. So just a little bit about me before we start. My name is Émilie Péloquin and I'm the Director of Global Advanced Product Support for Olympus. My background is in welding. I was working in the welding industry since 2009 and got my welding degree and decided after the fact to go into non-destructive examination and studied all the major NDT method with a bigger focus, of course, on ultrasound and later the advanced side of ultrasound, including phased array, FMC, and TFM. So here's the agenda for today, a very short agenda. So we'll look at what is a waveset. We'll also look at the advantages and the limitation of TFM inspection. Then we'll look at the right waveset for the right flaw, because this is really important and that's where I'll put most of the emphasis. And after that, some tools, including modeling for selecting the proper waveset. So first off, let's start with what is a waveset. You can hear also a mode of propagation or imaging path, depending on the code that you might be using or where you are in the world. So to go back just a little bit on what is FMC and what it does. So as opposed to phased array ultrasound, FMC actually does not form a wavefront during the transmission. So FMC is only firing one element at the time. So only one element is fired and the echoes generated within the component are recorded on all the elements coming back. So all of the elements of the array. So that means that all possibilities are recorded when we are doing FMC. So that's what FMC stands for, full matrix capture, and that's why it's really because it's recording the full possibilities for a given probe. So by including boundary reflection in the path from the transmitter to the receiver, discontinuities in the region of interest can then be imaged from a different direction. And as we know, with anything with ultrasound, the more perpendicularity we can have with an indication, the stronger the return signal is and the higher the probability of detection. So that's one of the advantage of FMC and TFM, is being able to change that direction to optimize how we're going to catch that indication. So here I am showing three different wave sets. We see TT here for transverse, very similar to a normal pulse echo using phased array. Then again, another pulse echo type of waveset, a 4T, which is basically like a second leg of phased array. And then something a bit different that we're not used to see as much when coming from a phased array background is a self-tandem mode using 3T. So here, what the sound is doing is that it's going to the back wall and then to the reflector to then go back within the probe. So there is two different main families of wave sets. We can see the pulse echo here on the left and the self-tandem. So as I mentioned earlier, pulse echo is a bit more similar to what we would see with phased array. L standing for longitudinal, T standing for transverse. And then for self-tandem, here are the newest, let's say, or the less common ones, where the sound again is often bouncing to the back wall once or multiple times and going to the reflector to then go back in the probe. You may also know these modes as direct or indirect for pulse echo and self-tandem. So the advantages of a TFM method, so flaw detection, but more specifically flaw characterization capabilities is what got a lot of people interested into TFM. So here I put it in parentheses, it's dependent on the selected waveset, which we'll look at in a few minutes. So as an example here for a pulse echo, we're looking at a root crack. So what we would be familiar to see with phased array here is something like a TT mode, where we're sending the sound to the indication and then coming back to the probe. So what we would see as a result from that when characterizing and we're looking at the signal is a strong, usually corner trap reflector with a fainted tip diffraction. So somebody that is used to look at phased array information or phased array data will understand that this is a connected flaw. As we know here, it's being a root crack. But for somebody that is unfamiliar, they might think that this is two different defects, or they might entirely miss that tip diffraction. With TFM here, using a different approach or a different direction for that path, using a 3T, for example, we're capable of imaging this reflector in a much better way. So now we know it seems obvious that it is one crack and one single indication. So again, the advantage certainly is on the accurate visualization for a given flaw. So here again, showing the ID crack using 3T. And here, a lack of sidewall fusion using a different mode called 4T. So capable of imaging very well, sitting on the weld bevel, that lack of sidewall fusion. But a limitation is also part of its strength. So basically, if I am not using the proper waveset, as I was showing 3T or 4T or others, for the proper type of flaw, then I might be missing the indication altogether. It might disappear from my screen. So one really easy way to show this, I've put a probe on a resolution block here with sidra holes. And I am showing here four different modes. So the first one being pulse echo, as we looked at before, very similar again to phased array. So the reflectors are showing very well, very round reflectors, nice amplitude, using TT, which is the proper waveset for this kind of for imaging this kind of reflectors. But then I switched to LL, again a pulse echo mode. I haven't moved anything. All I've changed is that I'm sending longitudinal waves through a shear wedge, so maybe not the optimal, but I can still see something. Now, as soon as I change for my indirect modes or my self-tandem modes, I can see that I'm losing everything from my screen. The reason for that is that it's expecting the signal to go and bounce off the back wall of the component, then going and bouncing on the reflector, and then coming back in my probe, which is not happening here. And so I can lose those reflectors entirely because I didn't have the right waveset. So not having the right waveset, what else can it create? So for a lack of sidewall fusion, here the same big reflector as we looked at earlier in 4T, here if I'm looking at it with 2T, I don't see anything. I'm losing it from my screen entirely, even if it's a very large reflector, of course from same side here. Going into 3T, same thing. I'm still not seeing that very large reflector because I don't have that nice perpendicularity with the returning signal. And then finally in 4T, now even from the same side of the indication, I can catch it very well. I can image it. It's a very strong reflector, very nicely imaged. For a root crack, as we saw again in TT, corner trap, tip diffraction, I can kind of see it. I can understand that this is something connected if I'm used to looking at phased array information. But it is also possible that somebody that would miss this tip diffraction signal. Then with 4T, well, very similar again as a second leg, still seeing the corner trap, but not much else. But then finally with 3T, we know it's the right mode for this kind of indication, for that root crack at that position. So I'm imaging it very well. So in conclusion, does this mean that the 3T is the perfect mode for vertical defects and that 4T is the perfect mode for angled reflector? Well, you probably have guessed it's just not that simple, because otherwise we wouldn't have all those other modes available, right? Unfortunately, there's more to this than saying vertical and angled reflector will be caught with a certain mode. The depth is also extremely important. So what I'm showing here is that for the same kind of vertical reflector, just like we had at the root earlier, for a toe crack, we're going to use an entirely different waveset, which is here a 5T, to be able to catch it at the surface. There's that very nice quote from Henry Ford that says, "Failure is simply the opportunity to begin again, this time more intelligently." So how do we inspect more intelligently with TFM? Is the option to try and try again, the trial and error until we find the right waveset? So why is experimental selection of a waveset just unfortunately not viable for TFM? The reason for that is that there is too many variables at play. As we saw, the type of flaw will change the waveset selection. The orientation of that flaw will also affect the waveset selection. The position or the depth of that flaw within our component will change what the waveset selection will be. And something I haven't touched on here, but the part geometry, the curvature of that part, for example, or the thickness of the material change or the velocity change within the material would all affect what kind of waveset we need to select for the right inspection. And so just for part geometry, for example, if we have a curvature, the sound will not bounce in the same way. So that same root crack that we use 3T, and we're so used to use 3T for that root crack, well, when it's a curved component, it's very likely that it's not going to be the proper waveset for that same root crack. So we need to be very careful in assuming which waveset is the proper one. So again, there is a lot of wavesets that are available to the user, commonly about 10 or plus. And so it becomes, again, too many variables to be able to do a trial and error. We need to know before we inspect. So what's the smarter way is by using modeling. So people that have been doing TFM inspection for a long time know that modeling is essential when using a total focusing method. It's the most effective way to predict the result for a given waveset, a given flaw, a given depth, material, velocity, geometry, frequency, all of those variables. It removes the guesswork out of the equation, of course, and it provides a reliable scan overview, so you actually know and you can see visually what to expect when you're going to inspect with a given waveset. It predicts also the dB that are going to be in the area of interest. So you know that if you see something that is very fainted, then potentially it can be normal, but also something to flag because it's likely to be still a relevant indication. So it provides a lot of information for a given inspection. So it's possible to model on board of the instrument. Here is a screenshot of the OmniScan X3 modeling tool. So I'll show very quickly what it would be to go around and select a waveset. So here's the tool on board of the equipment. And so you can see here that the TFM mode will provide this screen or this scan overview. And we have pulse echo and self-tandem showing different ones and the different flaws also that I can select. So I'll switch to planar here and I'll show here that a 30-degree, just like the bevel of this weld, but I can also change for something vertical. So vertical would be 0, and here you can see that for a root crack or something like that, I would not catch it with that mode. So if I change in a 5T with a self-tandem for a vertical reflector, as I showed earlier, at the surface, I'll catch it very well with that 5T. And so I know, again, that if there is something at the bottom of that weld, I'm not going to catch it with that 5T. So what I can do is also add multiple groups. I can go up to 4 different groups in TFM that I can view at the same time. So if I know that I want to cover the route as well, then I can go and create another group and another modeling for that section of my well. So that was a very quick overview of the tool, just to show how easy it can get and how now I can know for a given mode what to expect. I can create that also for a curved part, so I know how it's going to affect as well my inspection selection or my waveset selection. So truly, the modeling is the only reliable way for me to know exactly what I'm going to expect when doing a TFM inspection. So I hope that this was informative. If you have any questions, please feel free to reach out. This is my email address. So please, if you have any question about this presentation or TFM in general, feel free to reach out to us. Thank you very much.